filters, shopping recommendation algorithms, stock market forecasting, security programs, and healthcare interventions. It seems clear that there are some unique strengths of ML algorithms that outperform traditional inference models that make it so pervasive. But what are they? One of the primary areas where ML excels is in managing high dimensional data. In situations where the number of features of variables is significantly larger than the number of observations, classical statistical methods often struggle. And these traditional techniques can become cumbersome and inefficient, leading to suboptimal results. However, ML algorithms such as regularized regression, decision trees, neural networks are designed to handle high dimensional data more effectively. These algorithms also incorporate mechanisms to manage and prioritize these vast number of features that are harder for traditional methods. Another strength of ML is in its ability to automatically capture complex nonlinear relationships between variables. Linear statistical models are usually limited in their capacity to model these relationships, often requiring manual transformations or extensive tweaking. And in contrast, ML algorithms like decision trees or neural networks are really capable of identifying and modeling these nonlinear patterns. This also allows us to uncover some deep insights and make accurate predictions using large amounts of data. Unstructured data, which includes things like text, images, and audio, usually presents a significant challenge for traditional statistical techniques. And these methods typically mostly use numerical data. And so this makes it really difficult to analyze unstructured information effectively. However, ML, again, with things like neural networks, excels in this domain. ML algorithms can process, analyze, and extract valuable insights from this that result in a range of applications from social media related things to voice activated systems. And finally, many ML algorithms are designed to handle massive data sets with millions or even billions of data points. So they're built to scale horizontally, which means that they can distribute computation across multiple machines, ensuring efficient processing of large-scale data. On the other hand, statistical methods here can become computationally intractable and are faced when they're faced with such large volumes of data. All right, so now that we know the strengths of ML algorithms, I just want to add a little disclaimer because this topic is just so vast. And so I wanted to narrow down on what things that I will be covering. So I do want to add a disclaimer that my talk is not going to cover differences between R and ML, between Python and R for ML, and what method to choose and the pros and cons of using R. Instead, I'll be discussing the steps in building your own ML project and how R packages can play a role in each of these steps. The first step in building your ML project is to process your data. Effective data processing is the foundation upon which robust ML models are built. It ensures that our data is clean, relevant, and ready for analysis, leading to more accurate and reliable models. But what does this entail? The first is exploratory data analysis, which usually involves summarizing the main characteristics of data, often using visual methods or things like just looking at the mean or the range of values in the data set. Through this, we can identify patterns, spot anomalies, and formulate some sort of hypotheses based on our data set. This step is fundamental as it guides the subsequent pre-processing steps by revealing its underlying structure and relationships within the data. We can do this in R using a combination of dplyr, tidyverse, and ggplot functions. And I've outlined a small example here. The next is handling missing data. Missing data is a common issue in many data sets and can significantly impact the performance of machine learning models. We can remove records with missing values, though this might lead to loss of valuable information sometimes. Alternatively, we can also impute missing values using statistical methods like mean, median, or more techniques like multiple imputation using the MICE package and random forest-based imputation using the MIS forest package. Again, like I've added a small example here that you can look at. The next step is to address outliers, if there are any. So outliers are data points that deviate significantly from other observation, and this can distort our model's training and performance. So identifying and handling outliers is crucial to build robust models. In R, we can use statistical tests or visualization tools using functions like the box plot function here. And once identified, we can choose to remove these outliers or transform them depending on the impact they can have on the model. Finally, we have things like feature engineering and feature scaling that involves creating new features or modifying existing ones to improve the model's performance. This step is really crucial for extracting the most relevant information from our data. And in R, we can use either domain knowledge to try and transform these ourselves, like I've listed here. Power to weight is transformed as like a combination of two other features here. Or we can create some sort of terms and normalize them using functions from the caret. So for feature engineering, when we want to create new features or create mock features, we can use functions from the flyer or the caret package. And for feature scaling, which is a more normalization-oriented method, we can use functions from the caret package or the scales package. Finally, to evaluate the performance of our machine learning model, because it's a largely predictive algorithm, we need to split our data into training and validation sets. The training set is used to train the model, while the validation set is used to assess its performance. In R, functions in the caret package can help us divide the data set in a way that maintains the representativeness of both sets. And this step is very critical for ensuring that our model can generalize well into the real world. All right, now that we have a processed data set, it's time to pick and train our model. There are broadly two types of commonly used ML algorithms, supervised and unsupervised learning. Supervised learning models can train on a labeled data set, which means that each input is paired with the correct output. And unsupervised models work on unlabeled data, which and are powered to find patterns or structures that don't often have any prior guidance. Supervised learning includes tasks like regression and classification, and unsupervised learning includes tasks like clustering and dimensionality reduction. For regression, we have regularized linear models, random forest regression, gradient boosting regression using the XGBoost package, decision tree-based regression, and support vector regression. I've added a little snippet here that you can work through maybe later, and that just provides the starting functions for each of these packages and what goes into fitting these models. For classification, we have functions within the caret package itself, or we can use other packages that are built around random forest classifiers or gradient boosting classifiers, or regularized logistic regression-based classifiers in the GLMNet package. For clustering, we have k-means clustering functions that are built in with the stats package that is built into R. We also have the cluster package, and we also have another package for density-based clustering using the DD-scan method. For dimensionality reduction, there are lots of methods, but I've highlighted 3 here. So principal component analysis, which is one of the most commonly used methods, can be run this, we can perform this using functions in the stats package itself. The choice of the dimensionality reduction method, again, depends on the problem that you're trying to answer. I've also listed R-tificial if you work with biological data like me. It's one of the most commonly used methods for large biological data sets. Right. As you can see, each fundamental ML task has several options to pick from with lots of internal customizations. The choice of algorithm and package can depend on factors like ease of use, the level to which you want to modify things within it, and any secondary functions that you might find useful within these packages. We now move on to the last part, which is testing ML models using the test data set that we created in step 1. Classification tasks have metrics like accuracy, precision, F1 score, and area under the curve. We can calculate these using functions in the caret package and the PROC package to plot these area under the curve plots. Regression tasks have metrics like root mean squared error or RMSE and the R squared. Again, there are multiple ways to calculate these, but the easiest way that I find is to just write a simple formula in R and calculate these using the dataset. I'd like to end here by mentioning that ML methods can seem very daunting and confusing, but appropriate visualization techniques and good data processing practices can help us increase the confidence in using these. And we now know that it's possible to do these using several different ways in R. Thank you.